So what we'd like to look at here are the correlations for the Nusselt number and the resulting calculations for the rate of heat transfer from cylinders in a cross flow. So for this discussion, let's assume the following conditions. We'll have the free stream conditions where T infinity is 25 degrees C and U infinity is 10 meters per second. We'll assume a diameter. I have written here for cylinder and sphere because we can utilize this as well for a sphere, but the diameter will be 5 centimeters, so 0.05 meters, and we'll assume a surface temperature of 185 degrees. So this gives us a film temperature of 378. Now, for the different correlations that we're going to be using, some of the parameters will be evaluated at the film temperature and some will be evaluated at the free stream temperature, and at least one more will be evaluated at the surface temperature. So that's what I'm doing here, and I'm using, I won't call them subscripts, but I'll call them an indicator. So VF and KF and PRF are all the viscosity, the thermal conductivity, and the Prandtl number evaluated at the film temperature. So then the free stream temperature is 25 degrees, so that converts to 298 degrees Kelvin. You really could call this just 300, but since I have the interpolations already put out here, I can do viscosity. So nu INF is the viscosity evaluated at the free stream temperature. Same thing for K INF and the Prandtl number INF. For one of the correlations, we need to evaluate the Prandtl number at the surface temperature. So the surface temperature is 185 degrees, which works out to 498 Kelvin. And again, this is the interpolation for my Prandtl number evaluated at the surface. All right, so in the text, it presents 3 different correlations for the cylinder. And the first one is the Hilbert correlation. So in this correlation, all fluid properties are evaluated at the film temperature, and it's applicable for cases where the Prandtl number is greater than 0.7. So the form of the correlation is very much like the form that we've seen for the flat plate. We have a constant out front and the Reynolds number raised to some value and the Prandtl number to 1/3. So we'll evaluate the Reynolds number at the film temperature, and we get a Reynolds number of 20,000, or 20.8 times 10 to the 4th. So that brings us right in here, and we have a constant of 0.193 and the M value of 0.618. Now, the Prandtl number at the film temperature is 0.6944. So this correlation should only be used, or is deemed only applicable for Prandtl numbers greater than 0.7. So this is not strictly applicable, but I wanted to work it out anyway, just to give you an indication of how we do it. So we get the Nusselt number. So in the textbook, this is NU bar subscript D. I don't have a way of putting the bars on here, so this is the average Nusselt number with respect to the diameter, so it's being used for a cylinder, and we wind up with a value of 79, call it 79.8. So now the next correlation is the Zukowski correlation, and this one is a little bit more fussy, shall we say. The fluid properties have to be evaluated at the free stream temperature, and there is a value of the Prandtl number that also has to be evaluated at the surface temperature. This correlation does have restrictions with regards to the Prandtl number shown here and with the Reynolds number, and you have to take into account what the Prandtl number happens to be for an additional constant. We're rarely going to be dealing with any Prandtl numbers that are much larger than we'll usually be dealing with Prandtl numbers less than 10, especially for gases. When we get into liquids, or if you're dealing with liquids, you sometimes have to worry about or take into account that the Prandtl numbers might be larger than 10. But there isn't a large difference in terms of the power that you're raising to. So to utilize this one, we have to calculate the Reynolds number at the free stream temperature. So we see that it's increased a little bit with respect to this one, almost up a factor, a value of 10,000. So we have a different Reynolds number. Since we have Reynolds number of 3.1 times 10 to the fourth, we're still in here, so our constant C is 0.26, and the exponent is 0.6. The Prandtl number that we have in the free stream is 0.707, so that gives us an n exponent, since it's less than 10, of 0.37. We can go ahead and calculate these values, and we end up with a Nusselt number of 115.991, or 116. So it is considerably greater than what we got with the Hilbert calculation. So now the Churchill and Bernstein correlation is, while it looks like the most complicated equation, it's actually the sort of the easiest to implement, because all fluid properties are evaluated at the film temperature, and it's valid for all Reynolds numbers and for Prandtl numbers, all Prandtl numbers greater than 0.2. So there are much less restrictions on this one. So we go ahead and we evaluate it. We already have the Reynolds number at the film temperature calculated for the Hilbert correlation. So we get a Nusselt number of 80.4996, or 80.50. So what I'm doing here is I'm plotting these correlations as a function of the Reynolds number. I should add this in here. So the horizontal axis is the Reynolds number, and the vertical axis is the average Nusselt number. So I want to call your attention to what's given in the text here. So the authors state that they again caution the reader not to view any of these correlations as sacrosanct. Each correlation is reasonable over a certain range of conditions, and for most engineering calculations, one should not expect an accuracy to much better than 20%. So this is plus or minus 20%. And then he goes on to further say, because they are based on more recent results encompassing a wide range of conditions, the Zukowski and the Churchill and Bernstein are the ones that they generally use for the calculations in the text. So the text doesn't explicitly state it, but when you look at the plots, you can really see that the Zukowski forms an upper limit for the Nusselt number, and the Churchill and Bernstein form their lower limit. And the Hilbert is very close to the Churchill and Bernstein. It's divergent here at lower Reynolds numbers, but as the Reynolds number increases, they sort of lay onto each other. And you can see they're beginning to diverge as we get up to the larger Reynolds numbers. All right, so you have a sort of an upper limit and a lower limit. We have the Nusselt numbers. So now we can go ahead and determine the rate per unit length of the cylinder. So for the Hilbert, we said our Nusselt number is 79.77. Multiplying the Nusselt number by the heat transfer, the thermal conductivity of air divided by the diameter of the cylinder, we get a heat transfer coefficient of 51.257. And then we go ahead and multiply that by our area. Now we don't know the length of the cylinder, so what we're going to use is essentially just the value of the perimeter. So the perimeter of a circle is pi d. So we end up with the rate of heat transfer as being 12,088 watts per meter, and that per meter is per unit length of the cylinder. The Zukowski correlation we had the Nusselt number of 116. That gives us a thermal coefficient of a heat transfer coefficient rather of 60.64. And again, we're in this case for the Zukowski correlation, all the parameters are evaluated at the free stream temperature, so we have a different value of K here. And we end up with a value of 1,524 watts per meter. And then finally, for the Churchill-Bernstein correlation, the value is 80.5. The heat transfer coefficient rather becomes 51.7, and we end up with a total rate of heat transfer of 1,300 watts per meter. Now it's instructive to take a look at what's plus and minus 1,300 and plus or minus, 1,300. Well, let me just write it out here. If I go 1,300 times 1.2, I get a value of 1560. And then if I take the value of 1524 and multiply that by 80%, so the minus 20%, we get a value of 1219. So you can see that the values of the Churchill Bernstein and the Zukowski correlations overlap each other when you do a plus or minus 20% value. All right, so hopefully that gives you an idea of how you're using these correlations.